Hi everyone, my name is Shub, and today me along with Brahmi and Adesh, we're going to be teaching you a series convergence test, which is essentially chapter 10 of calculus. So first of all, what exactly is series? Series convergence is basically a concept in calculus which is very important because it helps us understand the behavior of infinite series, whether they converge or diverge, etc. And it's pretty important for solving problems in physics and engineering too. And because of the application of series, we decided to pick series convergence as our topic to teach. So first of all, I'm going to be going over some tests for series convergence or divergence. And the first test we're going to be looking at is test for divergence, which is also called the nth term test. The nth term test for divergence states that if the limit as n goes to infinity for an is not equal to 0, then the series of an diverges. Essentially, if the thing inside the series, if you take the limit of that as it goes to infinity, if that does not equal 0, then it diverges. What's important to know here is that you can't use the series for finding convergence of series, which basically means that if the limit of an is equal to 0, then that does not mean that it converges. You can only use this test to prove divergence. So one example is a series from n is equal to 1 to infinity for n over n plus 1. So you do the limit of the thing inside, so limit as n goes to infinity for n over n plus 1, and that's going to turn out to be 1, which is not 0. And since the limit is not 0, this series diverges by the divergence tests. So the series for n is equal to 1 to infinity for n over n plus 1 diverges. Second test we're going to be looking at is the geometric series test. The geometric series test is in the form a times r to the power of n, where a is going to be the first term and then r is the common ratio. So you determine the convergence or divergence solely based on the common ratio of the geometric series. So if the absolute value of the common ratio is less than 1, then it converges, but if it's equal to or more than 1, then it diverges. A tricky or something you should know for geometric series is that they might ask you to find the sum of geometric series, and you can use the formula a divided by 1 minus r to find the sum of the geometric series. So let me show you an example here. So for a series which goes from n is equal to 0 to infinity for 2 over 3 to the power of n, you get the first term to be 1, so that's the a value, and r is equal to 2 over 3. So the absolute value of r is equal to 2 over 3, which is less than 1. So since the common ratio is less than 1, you can say that the series n is equal to 0 to infinity 2 over 3n converges according to this geometric series test.
And now we'll be talking about the direct comparison test. The direct comparison test involves comparing a series to a known benchmark series. If the series being tested is less than or equal to the convergent series, it is also convergent. If the series being tested is more than the divergent series, it is also divergent. And just to point out that both the series have to be greater than 0. And one thing you should look out for when doing problems like these are ensuring that the n series is smaller than the bn series, because if that changes, then this test does not apply. Problem for the direct comparison test, and I rewrote the rules just for reference. So the practice problem we'll be working with is a series n over n squared minus cosine n to the power of 2. And the first thing we want to do is find a similar series. And the series that I found was using the dominant terms of the numerator and the denominator. And the numerator has a dominant term of n, and then the denominator has the dominant term of n squared, which equals to the series as n equals to 1 to infinity 1 over n. And this series diverges by the p-series test. And just to ensure that this series can be applicable to the direct comparison test, I can see that a of n is smaller than or equal to the b of n, and so by the direct comparison test, since a of n diverges, b of n also diverges.
Of the limit comparison test, which is really similar to the direct comparison test in that in both tests you have to choose a function to compare your given function to, except instead of directly comparing them, we are using a limit. You use a limit comparison test when you're not really sure if your chosen function is greater than or less than your given function. So here, all you need to know is whether or not your chosen function converges. So yeah, so our form is limit n approaches infinity, a of n, which is our chosen function, over b of n, our given function. And if the result of that limit is a positive and real value, or greater than 0 and less than infinity, both the series either converge together or diverge together. Problem for the limit comparison test. Series equals series n equals to 1 to infinity, 2 to the power of n over 3 to the power of n minus 1. Now we're going to use the limit comparison test on this. First thing that we have to do is figure out a series to compare our given series to. I chose 2 to the power of n over 3 to the power of n, just because it would probably follow our given series just because they're so similar. So plugging it into the formula for the limit comparison test, we have limit n approaches infinity, 2 to the power of n over 3 to the power of n, our given function, our a of n, divided by b of n, 2 to the power of n over 3 to the power of n minus 1. We simplify it and we end up with limit n approaches infinity, 1 minus 1 over 3 to the power of n. Now 3 to the power of n as n approaches infinity is infinity, so 1 over infinity is 0. So we end up with 1 minus 0, or 1, which is 1. Now, since our chosen function 2 to the power of n over 3 to the power of n converges by the geometric series test, which we covered earlier in the video, and since 0, because our given value from our limit is between 0 and infinity, by the limit comparison test, the given series S converges. Now, if it were found that whatever function that we have here does satisfy this bounds of being between 0 and infinity, but it diverges, that would mean that our series diverges as well. And if the value that we got here wasn't between this bound of 0 to infinity, we would know that these two series do not follow each other, and thus the limit comparison test is invalid, and you would have to use a different test.
We're going to be going over the alternating series test. It's basically a test used to determine if a series with alternating positive and negative terms converge. And they're usually in the form minus 1 to the power of n a sub n, or minus 1 to the power of n plus 1 a sub n. So the conditions for the alternating series test to converge are if the terms decrease, or a sub n plus 1 is less than a sub n, and the terms approach 0, or the limit of n approaches infinity, a sub n is equal to 0. So we're going to be going over a quick practice problem. So determine whether the following series converges using the alternating series test. And we're given minus 1 to the power of n over the square root of n. So our first step would be identifying a sub n, which is simply just 1 over the square root of n. And now we're going to see if a of n is decreasing over the entire series. And basically we can prove this by saying 1 over the square root of n plus 1 is less than or equal to 1 over the square root of n. And we can say this because as n increases, the square root of n also increases, so the entire 1 over the square root of n decreases. And our second step to seeing whether the series converges is to check if the limit of a sub n approaches 0. And so we write out the limit as n approaches infinity, 1 over the square root of n And that's equal to 0 because as n increases, the denominator increases, so 1 over the denominator approaches basically 0. And now, since both conditions are met, the series must converge under the alternating series test.
Please note that this video only covers some of the very important convergence tests. Thank you for watching!